Hello good people, I'm going to talk about significant figures. Significant figures, abbreviated SF, are the digits in a measured quantity that contribute to the accuracy. Measured quantities are values obtained by using a measuring instrument. Suppose that I have an enclosure for miniature space goats. The number of miniature space goats, in this case 12, is a count. It does not depend on any measuring instrument. The length of the enclosure, on the other hand, is a measured quantity, and it will depend on an instrument. According to the intervals on this measuring instrument, the length of the enclosure is somewhere between 8 and 9 meters long. Yes, the enclosure is longer than 8 meters, but the only thing I can say with certainty, based on this instrument, that it is 8 meters long. Anything else, and I'm guessing. This measurement would only have one significant figure, the 8 on the interval. If I wish to increase the accuracy of my reading and increase the number of significant figures, I need more intervals. Now I can make a more accurate reading. And based on these new intervals, I could say that the enclosure is 8.7 meters long. And so with the first instrument, I could say that the enclosure is 8 meters long, and I only have one significant figure. With the second measuring instrument, or more precisely with more intervals, I can say that the enclosure is 8.7 meters long, and now I have two significant figures. In a similar fashion, if I had 5 packets containing nondescript white powder, the number of the little packets would be a count, whereas the mass of a powder would be a measured quantity. This digital balance gives me only 3 digits. The mass of the powder is 125 milligrams, but I do not know is it 125.0, 0.1, 0.2, 0.3, simply because the instrument is not that accurate. It turns out that when it comes to reading, writing, and reporting of measured quantities, there are 5 rules that govern the significant figures. The first rule states that non-zero digits are significant. A value such as 274 has 3 significant figures. So the digit 2 is the first significant figure, the digit 7 is the second significant figure, and the digit 4 is the third significant figure. The second rule states zeros between other significant digits are also significant. A value such as 10,008 has 5 significant figures. The 1 and the 8 are significant because of the first rule, and the 3 zeros in between are significant because of the second rule. And so if I was to number these significant digits, it would be something like this. The third rule states that the zeros at the end of a whole number are placeholders and not significant. If I have a value such as 3,500, it only has 2 significant figures, the 3 and the 5. The zeros at the end are placeholders. They are here to indicate the magnitude of the leftmost digit. Right now, this 3 is in the thousand position. What these zeros are saying is that this value of 3,500 has been obtained by an instrument that is only accurate to the nearest hundred. The fourth rule states that leading zeros at the start of a decimal number are also placeholders and not significant. A value such as 0.0075 has only 2 significant figures, the 7 and the 5. The 3 zeros in front are leading zeros and they are not significant. Their purpose is to indicate the value of this 7 here. The fifth rule states that trailing zeros at the end of a decimal number are significant. A value such as 68.80 has 4 significant figures. The 6, both of the 8s, and the 0 at the end are all significant. What is the difference between 68.80 and 68.8? Firstly, in terms of significant figures, 68.80 has 4 significant figures, whereas 68.8 has only 3 significant figures. But more importantly, with 68.80, we are telling the next person that we have an instrument that is accurate to the nearest hundredth. Whereas with 68.8, we are telling the next person that our instrument is only accurate to the nearest tenth. Now I know at this stage you're probably wishing for some pick-me-up white powder, but if you stick with me for a few moments more, I'm going to talk about place values and also cure your insomnia. A place value is a value of a digit in a number based on its position. Each digit in a given number has a particular worth assigned to it. And so if I look at this number 3.141592, the 3 is in the ones or unit position, the 1 represents a tenth, the 4 a hundredth, the other one a thousandth, the 5 a 10,000th, the 9 a 100,000th, and the 2 is in the millionths position. By the same token, when it comes to the 169.735, I could say that the 1 is counting the hundreds, the 6 is counting the tens, the 9 is counting the ones, the 7 is counting the tenths, the 3 the hundredths, and the 5 the thousandths. When it comes to the yellow number, the 2 is counting the millions, the 7 the hundred thousandths, the 9 10,000ths, the 1 thousandths, the 6 hundredths, the 0 tenths, the 8 ones, and finally the 4 is in the tenths position. Why do we care about place value positions? Well, aside from giving us the magnitude of a particular digit, it also allows us to talk about these digits more precisely, and it will help with our rounding. But more on that later on. That is all for now, and I will see you on the flip side.